All right, Math 2, here we go. We got lesson 1.1.1, attributes of polygons. All right, so a polygon, hopefully you know this. Polygon is just kind of a shape where all of the sides are straight lines. So a circle wouldn't be a polygon because, it's made of curves. So a polygon would be a shape that's just made up of straight sides. So that'd be like your rectangle, your squares, your parallelograms, trapezoids, those kind of things. And on the first day of class, we just kind of generally went through with our polygon bucket activity. We went through all the, not all the different shapes, but, several of the different shapes. Before we get into the bottom part of these notes, we want to look at something called symmetry. So symmetry is where you can do something to the object so that it's still sitting on top of itself, so that it's the same exact type of object. There's several types of symmetry. We've got translational symmetry, reflectional symmetry, and rotational symmetry. So reflectional symmetry would be if I could draw a line somewhere on the shape so that if I folded the shape, it would be the same exact shape. What I mean by that is, let's look at this trapezoid first. Looks like it's an isosceles trapezoid. So on this one, if I were to make a line going right through the middle of the shape right here, I'll try to get as close to the middle as possible, but you get the idea. Yeah, it's about the middle. So kind of imagine in your mind's eye, if you were to fold it along this line, this point would be on top of this point, and this point would be on top of this point. And if I reflected it, this point would move over to this spot, and this point would move over to this spot. Basically, I'd just be kind of spinning it around that line, and it would be the exact same shape. So that's called reflectional symmetry, because it's going to be the same shape if I fold it across that line. So this one only has one line of symmetry, but it's possible to get a shape with multiple lines of symmetry. So we've got this shape over here. How many sides is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's a dodecagon, I think. So we got this dodecagon here. And if I were to do the same thing to this one, we would have reflectional symmetry. Because this would move to here, this would move to there, this would move to there, this would move to there. It'd be the same shape if I reflected it across that line. But that's not the only line of reflectional symmetry. I've done horizontal here. I could also end up going vertical. Do you see any other lines that I could reflect over? There are a couple more. You don't just have to go straight up or straight down. There are a couple more lines that we could do. We could go a diagonal line going through these 2 points. And we can see if we folded it across that. Ooh, that wasn't very good. I missed it. Good enough. All right, so if I folded across that line, this goes to here, this one goes to there. This one goes to here, this one goes to there. So it would be the same exact shape if I reflected it over that line. And then finally, I've got my last diagonal right here. And if I were to reflect over this diagonal, it'd also be the same shape. Some people are tempted to do this line right here, but that wouldn't quite work if you went from this point to this point. Because if you went across those, this one would not end up being in this spot. It wouldn't quite work if we did that. Okay, so that's reflectional symmetry. If we can reflect the object over a line, and it's still the exact same object, same facing, same everything. Rotational symmetry, as the name suggests, is when we can rotate it, and the object is exactly the same. So usually when we rotate objects, we rotate around the center, so like right in the middle. So like we're taking this object and we're like putting down our pencil right here. We're going to start spinning the object until it's the same exact facing. So here I've spun my paper 90 degrees and it's the same object. If I go another 90 degrees, same object. Another 90 degrees, same object. And if I go another 90, I'm back to where I started. So this one, we've got some rotation here that we could do. If I rotate it 90 degrees, you see how this is a 90-degree angle right there? If I start here and rotate it this direction, that's a 90-degree rotation. So this one moves to this spot, this one moves to this spot, this one moves to this spot, and so on. So that's a 90-degree rotation. But remember when I did that, I did a second 90 degree, and we got another rotation. So I could do a whole nother 90 and move this one all the way down to here. So I'll spin my paper and do that. 90, and then 90 plus 90, 180. So that would be a 180-degree rotation. And then if I did a third 90, that would be a 270-degree rotation. So this one looks like we could do it 3 different ways. We can do a 90 degree, we can do a 180 degree, and we can do a 270 degree. And you might be saying, Mr. Holcomb, but what about a 360? Well, yeah, everything is 360, because if you do 360, you're just back to where you started. But these are the ones that we're looking for. So 90, this one goes to here. 180, this one goes all the way to here. 270, this one comes all the way over to there. So that one's not too bad. Now this one, same deal. We've got, looks like a regular pentagon. And let's say that we were going to take this point here and rotate it until it were at this point here. So if I did that, it looks like it would be the same exact object. So I'm just taking this point and move it to there. That would look something like this. Now that's not 90 degrees. You can tell if this would be 90 because this is turning my paper sideways. And that's not quite the same shape. It's a little bit less than 90. So how many degrees is that? Well, what we can do is we can look at how many sides we have. And this is how many times we can rotate it. I can rotate it once, twice, 3 times, 4 times, and then a last time to get it back to 360. So to go all the way around, that's 360 degrees. So if I did 360 degrees and divided by the number of sides, which is 5, that comes out to, what's that, 72 degrees? Yeah, it's 72 degrees. So this means every 72 degrees, this shape is the exact same shape when it's rotated. So from here to here, instead of 90 degrees, this is only 72 degrees. If I go from this point all the way and rotate it to this point here, that's 72 plus another 72, that's 144 degrees. So our first rotation would be 72 degrees. And then to get from here all the way over to here, that's another 72 degrees, it's 144 degrees. If I added another 72 degrees to get this point all the way over to here, 144 plus 72 comes out to 216. So I've rotated here, here, and then all the way to here. And then it looks like I can get another 72 degrees. So do 1, 2, 3, 4 72s. That would be 288 degrees. And then the last one, if I add 72 to this, I'm back at 360, and we don't count 360. So this one looks like I can rotate it 4 different times for 4 different degrees. And basically, if you've got something that's regular like this, you can just take the number of sides and divide, or 360, and divide by the number of sides. And that'll tell you how much you can rotate, or how many degrees it takes to rotate to go one space. All right, so that's rotational symmetry. We're rotating it around a point, and it's the same exact object. All right, Venn diagrams. So in a Venn diagram, you've usually got 2 circles that overlap, and then you've got 4 sections to it. So we've got conditions. Anything in just this A part, not B, just the A part. That means it satisfies condition 1, but it doesn't satisfy condition 2. Part B means it satisfies both conditions. So whatever our thing is, it works for both. Part C works for condition 2 but doesn't work for condition 1. And then part D doesn't work for either condition. So looking at this polygon bucket that we did the other day, all those different polygons that we're looking at, all these named polygons, we're going to try to see where these polygons fit on this Venn diagram. So the Venn diagram is, on this condition, has at least one pair of parallel sides. Okay, so several of those shapes have at least one pair of parallel sides. Now I know that none of these in here are going to be triangles. Triangles can't have parallel sides. So that's not going to work. So no triangles can show up over here. And that means no triangles can show up here in this middle section, because this middle section satisfies this condition and this one. Has at least two sides of equal length. Now there I can get some of my triangles, because like I can get equilateral triangle that has three sides. I can get an isosceles triangle. I can get an isosceles right. And that would fit in here, but they don't have one pair of parallel sides. And then down here in this section, this would be has at least one pair of parallel sides and has at least two sides of equal length. So let's go ahead and take a look at how this might show up. So here I've got our Venn diagram. This first condition, remember, was has at least one pair of parallel sides. This one was has at least two sides of equal length. Now let's see what we've got here. A trapezoid is in this section. A right trapezoid is in this section. You might be asking yourself, well, Mr. Holcomb, why am I not putting a square right here? Because that has at least one pair of parallel sides. I'm not putting a square here because a square also has at least two sides of equal length. So that's why it goes in the middle here, because a square has parallel sides and it has sides that have equal lengths. Parallelograms have parallel sides and at least two sides of equal length. Rhombus, parallel sides, sides of equal length. Regular hexagon has parallel sides and sides of equal length. Anytime you see that word regular, that means that the sides are congruent to each other. Isosceles trapezoid, that does have parallel sides and it does have two sides that have equal length. Remember with the isosceles trapezoid, we've got parallel sides here, and then in an isosceles trapezoid, these two have equal lengths. All right, and a rectangle fits in this section. Now over here, these ones have two sides of equal length, but they don't have any parallel sides. So we talked about this earlier, equilateral triangle. It has three sides, but this has at least two, so that works, but no parallel sides. Isosceles triangle, that has two sides of equal length, no parallel. Kite, it does have two equal sides, but it doesn't have any parallel sides. Regular pentagon, that's going to go ahead and fall over here because a pentagon has, since it's regular, it has equal sides, but a regular pentagon, we can see here, no parallel sides on this one. None of these sides are parallel. So it can't fit in the middle, it has to fit over here. Now what doesn't fit in either one of them? Well, up here at the top, we've got a scalene triangle. None of these sides are parallel because it's a triangle. And since it's scalene, none of these sides are equal length. What else doesn't work for either of them? A scalene right triangle wouldn't work. And then just the quadrilateral. So this is just a quadrilateral, nothing special about it, nothing's parallel, none of the sides are congruent to each other. So remember, this middle section works for both. This section only works for this side over here. This section only works for this side here. The bottom section doesn't work for either one of them. All right, next one. First situation has only three sides, so those are going to be our triangles. Over here has a right angle. Okay, so let's look at our grouping here. Has only three sides and has a right angle. 3 sides, no right angle. So that would be over here, 3 sides but not right angle. Let's look at 3 sides with a right angle. Okay, 3 sides and it has a right angle. So this would go in the middle there because it has a right angle and 3 sides. This one, 3 sides, no right angle. This one, a right triangle, has 3 sides and a right angle. That goes in the middle. So when we're going to do this one, this is going to have the triangles, and this will have the right triangles. This will have all the other shapes that have 90-degree angles. So which other shapes have 90-degree angles? Well, it looks like the rectangle has 90-degree angles. The square has 90-degree angles. The right trapezoid has 90-degree angles. And that might be it. So let's look at what that one looks like at the end. So it has only 3 sides. Equilateral triangle, isosceles triangle, scalene triangle. This section, which one has 3 sides and right angles? The scalene right triangle and the isosceles right triangle. Okay, which ones only have right angles? Square, rectangle, right trapezoid. Which ones don't have 3 sides and they don't have right angles? That's a lot of them. Parallelogram, trapezoid, rhombus, quadrilateral, kite, regular pentagon, regular hexagon, isosceles trapezoid. Let's just take a couple of those. Let's look at the rhombus and let's look at the regular hexagon. So, regular hexagon doesn't have 3 sides, so it doesn't do the first one. And a regular hexagon does not have any 90-degree angles in it. So that's why it doesn't fit in either one of them. Rhombus doesn't have 3 sides, and these angles can't be 90. If they were 90, it'd be a square instead. So that's why those are down there. All right, last one. Has reflectional symmetry. Okay, reflectional symmetry, what was that? It means if we draw a line, it'll reflect on top of itself. Okay, so it does have reflectional symmetry and has 180 rotational symmetry. Okay, let's just go back to ours and look at them. Okay, here's this one, no reflectional symmetry. I can't cut this in half, and I can't rotate that one either. Kite, can I cut it in half? Yes. If I cut it down along this line, I would have reflectional symmetry. But if I spin it 180 degrees, that's not the exact same shape. It's facing the wrong direction. See, this long side's pointing down. When I rotated it 180 degrees, it was pointing up. So this one has reflectional symmetry, but not rotational. This one has both. I could cut it straight across here, and then it would have reflectional symmetry. I can also spin it 180 degrees. That means if I spin my paper upside down, it's the exact same shape. So it has 180 degree rotation. Let's see. Nope. Quadrilateral, I can't reflect that. I can't spin it. Trapezoid, nope. Rectangle, yeah, I could cut that in half and it'd be the same. If I spin this 180 degrees, would it be the same? Sure would. Rhombus, yep, I can cut it in half and it'd be the same. And if I spin 180 degrees, it'll also be the same. So that one works for both. Can I cut this one in half? Yep. Can I spin it 180 degrees? Yep, I can do both of those. Can I cut this one in half? No, there's no real good place to cut this one in half. That's not going to work. If I rotated 180 degrees, would it be the same? No, this would be pointing down instead of pointing up, so that wouldn't work. What about this one? Rotated 180 degrees, nope, this point would be pointing up. But since it's isosceles, if I cut it directly down the middle here, it would have reflectional symmetry because it's isosceles. Same thing with this one. It's isosceles, I can reflect it right down here. And it's the same. But I can't rotate it because this pointy part would be pointing down if I went 180 degrees. What else do we got? Parallelogram. If I rotated a parallelogram Reflected a parallelogram, does that work? No, that doesn't work. So I can't just draw a line and reflect it, because when you reflect across a line, like you might be thinking, hey, why don't we just go right down the middle kind of diagonally? You have to go 90 degrees to the line, and this would be off. It wouldn't be on top of each other. It kind of looks like it might work, but here, just let me do this. If I do like the line right here, this point has to go 90 degrees. So this point would be all the way over here somewhere. It has to go perpendicular. So if I tried to cut it right there, it wouldn't be on top of itself, because this point would reflect over to here, and that's not on top of itself. So reflection doesn't work, but 180 degrees does work. Watch, if I spin this 180 degrees, same shape. See how it's leaning towards the right? If I spin it back, still leaning towards the right. So it has rotational, but it doesn't have reflection. I can reflect this one. 180 degrees doesn't work. This would be pointing down. This one does not work for either. This one, I can cut it in half, but if I rotate 180 degrees, the pointy part would be pointing down instead of pointing up, and that wouldn't work. Isosceles trapezoid, I can cut it in half and make it a reflection, but if I rotated 180 degrees, the long side would be on top and the short side would be on bottom. That wouldn't work. So to finish this off, here's what has reflectional symmetry. Equilateral triangles, we talked about how we could draw a line right down the middle. Isosceles, isosceles right, kite, regular, isosceles trapezoid. Which ones have both, rotational and reflectional? Square, rectangle, rhombus, regular, hexagon. Which one only has 180 degree rotational symmetry? This is interesting. The parallelogram is the only one that just does 180, but it doesn't do reflection. It's kind of different. And then there were a few of them that didn't do either one of them. That would be a scalene triangle. You can't reflect it. You can't rotate it. Scalene right, can't do either one. Trapezoid, you couldn't. Quadrilateral and right trapezoid, you could. So really remember what we're looking for in this section is for you to know your shapes and know where the parallel sides are, know where you have right angles, and know where you have congruent sides, sides that are measured the same. And then on top of that, we're adding this thing about symmetry, making sure that you understand what reflectional symmetry, when you draw a line and you reflect, which is make the mirror image, and it's the same shape. Rotational symmetry, that's when you spin the image and it's still the same shape. When you do a rotational symmetry, you need to make sure you're saying how many degrees you're spinning it. Remember what we said? We said if it has a number of sides, you can take 360 and divide by the number of sides, and that'll tell you how many degrees you need to spin it to get it on top of itself. All right, that is all the math I have for you today. Math hard. See you guys later. Bye-bye.